All right, let's dive in. Today, we're looking at a material that could literally change everything. I'm talking about transparent armor, next-gen medical implants, you name it. The material? Nanoceramics. And there's been this absolutely stunning breakthrough that finally cracks a problem scientists have been wrestling with for decades, taking this stuff from a cool idea in a lab and making it something we can actually build with.
So, what's all the fuss about? What's the big promise here? Well, to really get why this new technique is such a big deal, you first have to understand what makes these materials so incredibly special to begin with. And really, it all boils down to what they look like on a microscopic level.
Okay, so a nanoceramic is basically a ceramic where the little crystals or grains that make it up are ridiculously small. We're talking less than 100 nanometers. The source material had this great way of thinking about it. Picture a city, but instead of giant skyscrapers, this city is made up of millions of tiny little houses. Now, in a city like that, what do you have a lot of? Sidewalks, alleys, right? Little pathways connecting everything. Those are the grain boundaries. And in a nanoceramic, those boundaries make up a huge part of the material. And that, well, that changes everything about how it behaves.
Yeah, this structure gives them what are basically superpowers. I mean, they can become super plastic. Think about that for a second. A ceramic that can stretch like taffy without shattering. That's just unheard of. On top of that, they're way harder, way stronger, and you can even make them optically transparent. And it's all thanks to those tiny, tiny grains and that massive network of sidewalks connecting them.
Okay, so if this stuff is so amazing, you're probably wondering, why isn't my phone made of it? Why are we using it everywhere? Well, there's a catch. A really big one, actually. It's a fundamental problem that's had scientists scratching their heads for years. You could call it the sintering paradox.
See, the catch is all in how you actually make something out of them. You start with this super fine powder of nanoparticles, but to turn that dust into a solid, useful part, you got to heat it up. That process is called sintering, and that's where it all tends to fall apart.
The source material puts it perfectly. It's like trying to bake a bunch of tiny, intricate cookies. You have to get the heating there fast enough to set their shape, but if you're too slow, they all just melt together into one big, boring cookie blob. See, the very thing that makes the nanoparticles want to stick together, this high surface energy they have, also makes them want to grow and merge into bigger grains when they get hot. And poof, there go all your special nano properties. You're just left with a regular old ceramic.
So that's the paradox, right? The very process you need to make the material, the heating, is the exact same process that threatens to destroy what makes it so special in the first place. You are in a race to fuse those tiny particles together before they get a chance to grow and ruin everything.
And that paradox? It kicked off a massive technological race against the clock. For decades, scientists and engineers have been trying to come up with faster, smarter ways to get the heat in there, anything to win this race against grain growth.
You can really see the evolution here. We started with these old-school conventional furnaces, right? They just bake the stuff for hours, way too slow. Then came a big leap forward, a technique called spark plasma sintering, or SPS. Now this was clever. Instead of heating from the outside, SPS zaps a powerful pulsed electric current right through the powder itself. It's super direct, super intense, and it cut the time down from hours to just minutes. Plus, it saved a ton of energy.
Now, SPS was a massive improvement, no doubt about it, but it still wasn't the final answer. The real holy grail, the ultimate goal, was to get the whole thing done in mere seconds. If you could just do that, you could basically freeze that perfect nanostructure in place before it had any chance to grow.
And that brings us to the flash of genius that finally cracks the code. It's a new, hybrid technique with a bit of a mouthful for a name: net-shape flash spark plasma sintering. Let's just call it NSFSPS. And trust me, it is an absolute game changer.
So here's the machine, and at first glance, you might think, hey, that just looks like a regular SPS machine. But the real genius here is in one tiny, almost ridiculously simple modification. They coated the inside of this graphite mold with an electrically insulating spray. That's it. But that one little change gives them an unbelievable amount of control over exactly where that powerful electric current goes, and by extension, where the heat gets concentrated. And this is where that control is just so brilliant. Look at this. If you've got a conductive material, like the nickel on the left, the setup forces the current to go right through the sample. Zap! But what if your material is an insulator, like the alumina on the right? No problem. The machine cleverly routes the current around the sample through some graphite foil, basically creating a tiny, personalized, ultra-fast oven. It works for anything. This adaptability is what makes it so revolutionary.
So what does this level of control get you? Well, it creates something they call a forced thermal runaway. All you need to know is that it generates just mind-blowing heating rates. I mean, just look at this chart. SPS was already pretty fast at about 1,000 kelvins per minute. This new NFSPS method, it hits up to 10,000 kelvins per minute. That is a full 10 times faster. Insane.
And the results of all that speed? Look at that number. The entire process, from loose powder to a solid, dense part, is over in as little as 8 seconds. 8 to 35 seconds, tops. The race against grain growth, they didn't just win it, they lapped it.
Okay, so they did it fast. But what about the final product? What does a nanoceramic that was made in less time than it takes to make a cup of coffee actually look like? Are the properties really there? Well, let me tell you, the results are just beautiful.
The proof is in the pudding, or in this case, the microscope image. Just look at these samples of zirconia. On the left, that's what you get with a more standard approach. See those big, chunky, coarse grains? That's exactly what you don't want. Now look at the right. That was made with the new forced mode. It's just perfect. Incredibly fine, totally uniform. That right there is the nanostructure you've been dreaming of. The difference is literally night and day.
And hey, the numbers don't lie. They back up exactly what we're seeing. We're talking near-perfect densities, over 95% for all these different materials, and they're doing it in seconds. This kind of performance across the board, I mean, just a few years ago, this would have been pure science fiction.
So, the big question, why does any of this matter? It matters because this isn't just a cool lab experiment anymore. This breakthrough finally unlocks the door to mass producing these amazing materials. We're talking about real-world stuff here. Transparent armor that's stronger than steel, cutting tools that never get dull, medical implants that last a lifetime, components for better batteries, more powerful lasers. The list just goes on and on.
Look, this technique is a fundamental leap forward. It takes nanoceramics from being this exotic what-if material stuck in a research lab and turns it into a scalable industrial reality. It's here, and it really just leaves you with one very exciting question to think about. Now that we can make materials this advanced, this fast, what are we going to build with them?